Hey everyone, and welcome to this explainer. If you are just taking your first steps into the world of reverse engineering, well, you're in exactly the right place. Today, we're going to completely demystify this whole process. We'll show you how to take a task that seems totally impossible and turn it into a highly structured, super manageable workflow. And we're going to do that by breaking down two absolutely essential technologies, Hex-Rays and FLIRT. I am really thrilled to guide you through this, so let's jump right in.
So let's be real for a second. Have you ever opened up a compiled executable file and just felt completely lost? Maybe even a little bit panicked? If you have, I really want to validate that feeling right now. Facing this massive wall of raw, unnamed assembly code is incredibly intimidating when you're starting out. Honestly, it looks like an uncrackable alien language. But don't worry, that overwhelming feeling is totally normal, and we are going to fix it today.
Okay, let's dive into this. Here's the clear roadmap we'll use to navigate from panic to absolute clarity. We'll cover the reverse engineering challenge, filtering the noise with FLIRT, translating the code with Hex-Rays, how they form the ultimate tag team using cloud power with Lumina, and finally, your next steps.
All right, Section 1, the reverse engineering challenge. Let's talk about what actually happens when you open an unfamiliar executable file.
We call this the code bloat dilemma. What's really interesting about this slide is that when you open a binary, you might see thousands of functions, right? But up to 75 or even 80% of that code isn't even unique logic. It's just standard compiler runtime libraries, standard template libraries, and open source dependencies. As a beginner, you definitely don't want to waste hours trying to reverse engineer a standard memory allocation function.
And to make matters worse, we usually have to deal with what are called stripped binaries. Commercial software, and especially malware, are almost always distributed in this stripped format. Basically, all the helpful debugging symbols, source code markers, and human-readable names, yeah, they're gone. They've been stripped away to optimize file size or hide proprietary details. This means you're left staring at generic, completely meaningless memory addresses like sub_41A20.
Which brings us to a phrase professionals actually use in the field, cognitive drowning. It literally feels like you're trying to sift through an endless ocean of assembly instructions. It's so frustrating to spend hours on this manual hunting expedition just trying to map out basic string manipulations before you ever even find the real malicious payload. It's exhausting.
So, Section 2, FLIRT, filtering the noise. Let's introduce the ultimate automated filter that shrinks that massive haystack down for us. Enter FLIRT. This stands for Fast Library Identification and Recognition Technology. It's an automated code recognition system built right into IDA Pro. Think of FLIRT as your first absolute essential tool. Its entire job is to scan the binary, automatically detect known third-party library functions, and label them for you. It separates what the developer actually wrote from what was just imported from the outside.
Just look at the visual contrast here. Without FLIRT, you're stuck looking at generic labels like sub_40 You've literally no idea what they do. But after FLIRT runs, bam! Those abstract placeholders instantly transform into semantically meaningful standard functions like malloc or memcopy. You can immediately, safely ignore them and focus your attention on the good stuff. It is literally like turning on the lights in a dark room.
Now you might be wondering, how does it actually pull this off so accurately? Well, the technical mechanics are pretty clever. It scans the raw machine code, sure, but compiler shifting's around in memory. So FLIRT applies an execution mask to filter out those volatile, fluctuating memory addresses. Then it computes a checksum only on the stable opcodes, the parts of the instruction that never change, and matches those reliable byte-level patterns against its massive signature database.
Moving right along to Section 3, Hex-Rays, translating the code. Let's talk about what we do with the unknown, custom code that's left over after FLIRT does its thing. This is where the Hex-Rays Decompiler shines. Think of it as your universal translator. Instead of forcing you to manually trace processor registers line by line, which, let's face it, takes immense expertise and time, Hex-Rays converts that low-level assembly language back into a readable, high-level pseudo-C representation. It completely abstracts away the hardware-level operations.
And this brilliantly illustrates exactly what I mean about the power of this translator. On the left, raw assembly. You have to think about moving data into the EAX register, adding 10. It's super tedious. But Hex-Rays instantly transforms that into readable logic. Result equals input plus 10. It takes those complex machine-level operations and turns them into logic you can actually read and understand in a second.
By doing this, decompilers clearly reveal the underlying logical structures, variables, loops, conditional if statements, arithmetic, and function calls. For a beginner trying to spot risky programming practices like buffer overflows or authentication weaknesses, this is a real game changer. It makes finding vulnerabilities incredibly fast.
Which brings us perfectly to Section 4, the ultimate tag team. Here is how these two tools combine to create a totally frictionless workflow.
I want you to focus on this number for a second, 300. Let's do some simple tag team math. Say you open a binary with 1,000 total functions. You run FLIRT, and it automatically filters out 700 library functions right off the bat. That leaves you with exactly 300 unknown custom functions. So instead of analyzing 1,000 functions, Hex-Rays now only needs to translate those 300 custom ones. You've literally just saved days of work in a few seconds.
So the crucial point here is this. Clean pseudocode relies entirely on accurate type inference and function signatures. If the Hex-Rays Decompiler has to guess what arguments a function accepts, you're going to get messy, distorted code. But because FLIRT runs first, it feeds the exact functional prototypes right into Hex-Rays. The translator knows exactly what it's looking at, giving you pristine, highly readable pseudocode. They absolutely need each other.
All right, Section 5, Cloud Power with Lumina, because modern reverse engineering definitely scales beyond just local files.
Since software development moves so incredibly fast today, local signature databases can sometimes struggle to keep up with every single new compiler version. Enter Lumina. Lumina is a centralized, cloud-driven metadata lookup system. When it finds a function, it computes a structural hash and queries a massive cloud database. If there's a match, it instantly pulls down function names, exact types, and even crowdsourced comments from senior engineers globally. It's collective intelligence right on your screen.
So, comparing the two, FLIRT is your traditional, local powerhouse. It uses .sig files and executes entirely on your local machine. Lumina is your modern cloud connection, relying on distributed metadata. And hey, if you're working in a highly secure corporate or defense environment, Hex-Rays even offers private Lumina. This lets highly secure teams run that massive intelligence database entirely on premises.
Finally, Section 6, Next Steps for Beginners. Let's bring all this together with some actionable advice for your very first malware triage.
I like to call this the golden workflow. Step 1. Always unpack your binaries first. Packed executables hide the original code structure, and FLIRT just can't read them until they're unpacked. Step 2. Run FLIRT to instantly filter out the standard library noise. Step 3. Visually isolate and focus only on the unidentified unknown functions. And Step 4. Unleash the Hex-Rays Decompiler on those specific unknowns. Stick to this step-by-step workflow, and you'll save yourself so much time. Also, if you're watching this and wondering how to scale these tools across a larger enterprise environment, you don't have to figure it out alone. Partnering with an expert solutions provider like ESPIN is a great move. They ensure smooth deployments by providing tailored enterprise licensing, secure private server architectures, and the crucial technical training your team needs for these advanced workflows. And that wraps up our explainer. But before we go, I want to leave you with one final provocative question. Now that you've got the ultimate tag team of FLIRT and Hex-Rays, now that all that standard library noise is filtered out and the complex assembly is finally translated into readable code, what vulnerabilities will you find first? You're no longer drowning in assembly. You're empowered to actually analyze. Thank you so much for joining me, and happy reversing.